The equation for Laplace transform looks like this, wherein if you apply Laplace transform on f of t is a continuous time signal. Okay, and if you apply Laplace transform on this, you will get f of s, which is the signal in, or which is in Laplace domain. Okay, so how does that look like? It looks like the 0 to infinity f of t power minus st, and we go from 0 to infinity because for circuit applications we need just integration from 0 to infinity. We don't consider it from minus infinity to plus infinity. Just for your information, if you're going from minus infinity to plus infinity, it is bipolar transform. If you're going from 0 to infinity, it is unipolar transform, only on the positive side, whereas here it is both positive and negative side of the time axis is included. Okay, and we also saw the basic signals. There are so many different types of basic signals, say unit step signal or function. Signal and function mean the same. Signals are also called as functions because signals are functions of time. See, f of t, it's a function of time, right? So it is called as function also. So it is unit step function, unit impulse function, unit ramp function, sinusoidal functions or sinusoidal signals or exponential signals. So they're all different basic signals we saw. We have not seen them in detail. I've just given you the names of that. We started looking at the Laplace transform on these basic signals. Okay, we have seen one basic signal, that is unit step function, fine, which is denoted as u of t. And how does it look like? It looks like this. This unit step function u of t is 1 for t greater than or equal to 0, and it is 0 for t less than 0. So that is what is your unit step function. Okay, and what would be the transform of Laplace transform of unit step function looks like? Okay, we need to look at, okay, how x of s is the equation for Laplace transform, fine. And in this place, in place of x of t, we need to have u of t. Okay, in the next place, what we are doing, in place of u of t, we are substituting 1. Why? Because see, u of t is 1 for t greater than or equal to 0. Greater than or equal to 0 means what? From 0 to infinity. So from 0 to infinity, u of t is 1. Okay, into e power minus st is that. Just integrate this particular exponential and apply the limits. Understand? And after doing that, we have seen that the what the transform happen to be what? What is that? Laplace transform of. It is there. It is not to be seen. I'll just do that here. Okay. So Laplace transform of u of t is 1 by s is what we have obtained yesterday. Okay. So the next uh, signal that we're going to take today is this. Everybody just observe this. The second signal, everybody you can just take down. Second signal that we are seeing, the basic signal, is unit impulse function. Okay, it's unit impulse function. Okay, it is denoted by delta of t. It is denoted by delta of t. Since it is denoted by delta of t, it is sometimes called as delta function also. Understand? So what is this delta function? Okay, just understand this. This delta function, this is defined as delta of t equal to, see here, it is 0 for t not equal to 0, and it is infinity, or we can call it as undefined. There is something which is not defined at t equal to 0. This is how we defined. So how does it look like? It looks like this, everybody. At t equal to 0 only it is going to exist, but what is it that is existing there? It is something which is undefined. What is that is undefined there is something to be seen now. Okay, I'll be giving you that now. Fine, it looks like this. So let's say this is the axis, x-axis and y-axis. This is t. So this is at t equal to 0. Fine. So this is, see here. So this is what is your delta of t. Understand? And we write 1 here. This is not a signal of what? Amplitude 1. This 1 indicates that it is area under the impulse. This is impulse. What is impulse? What is impulse? What is impulsive? Within no time, something comes and it goes off. So that means delta of t rises to infinity. This arrow says that it is going to infinity and drops down to 0 at t equal to 0 only. This is practically not possible. Practically not possible, but considering this signal would help in understanding some theoretical concepts and in deriving some results in signals and systems. Understand that? That's why this imaginary signal is also studied along with the other basic signals. Understand that? So this is delta of t, which means that its amplitude is infinity at t equal to 0. Okay, and this one says that the area under the impulse is unity. That's why it is called as unit impulse function. This one is the area under the impulse. Where is the area? Area is not to be seen there. There has to be some width and there has to be some height. Height is there which says infinity, but width is not to be seen. Width is tending to 0. Okay, so we shall see this in more detail in the next semester. We shall not spend time on this now. Okay, understand? Okay, there is a signal delta of t which is called as impulse function, and this is how it is going to look like. What it says, delta of t is 0 for t not equal to 0, and at t equal to 0 it is undefined. It is infinity. Infinity is undefined. I don't know what is infinity. Is it 100? Is it 200? Is it 10 lakh? It is 1 crore? No, we don't know. It's something which is not defined is your infinity. We all understand that it's very big. We all have seen it as a very big thing. Okay, what is that big? What is that equal to? Never, nobody knows. So it is undefined. Understand that? So infinity means some people call it as infinity, but you should understand it is infinite. Okay, so what happens if we apply the Laplace transform on this? Okay, so let's see. Okay, so therefore, Laplace transform of delta of t is given by what? It is 0 to infinity. In place of x of t, you will have delta of t e power minus st. Okay, and where is this delta of t existing? Where is this delta of t existing? This exists at t equal to 0, isn't it? That's why we say that this integral is evaluated as e power minus st, okay, where t is evaluated at t equal to 0 because delta of t exists at t equal to 0. So you're not supposed to integrate it. You're not supposed to integrate it as we did here. Okay, because delta of t is something that is undefined. So we have to be using something called as properties of unit impulse function to evaluate this integral, which we'll be doing in signals and systems, not here. Just understand, this is called as shifting property. Okay, so by shifting property, this is called as shifting property. Okay, so this particular entity, what we have got is got by something called as shifting. It's not shifting, it's SIFT only. By shifting property, this is true. So which means that it is e power minus s into 0. So it's e power 0. So it's 1. So what is that we've understood? Therefore, we can say that Laplace transform of delta of t is 1. Okay. So you may not be very comfortable to do this because we have not used normal integration here. Instead, we have used something called a shifting property, which I have not dealt with in detail. But for the examination sake, as of now, just understand that if there is any signal along with delta of t, dt is not written here. And if you are integrating that, Okay, if you integrate that with respect to dt here, any signal which is there along with delta of t, okay, and if you're integrating, that means this signal which is there along with delta of t needs to be evaluated at t where delta of t is existing. Where delta of t is existing, it's existing at t equal to 0, right? So this has to be evaluated at t equal to 0. That is what is called shifting property. Okay, don't worry much about this. Just remember this is what is going to happen if you integrate a delta function along with some signal. In this case, it is exponential. Okay, so what is important here is we should remember the Laplace transform of unit impulse function is 1. Okay, and similarly in the last class you've seen Laplace transform of unit step function is 1. Why do we call it a step? See here, it's like a step. If you see this waveform, it's like a step. So it is called as unit step. Why it is called as unit step? Because this step has got the height of amplitude 1 throughout, beyond t equal to 0, t equal to 0 and t greater than 0. Understand that? Okay, so we shall see another signal. Now what we are doing here is we're just trying to obtain the Laplace transform of the basic signals that we had listed in the last class. Okay, so let's take another basic signal now. What is that? Unit ramp. Everybody take down this. The third function that we are looking at is unit ramp function. Okay. Now, what is that unit ramp? It is denoted by R of t, mind you. It is denoted by R of t. What is this R of t? This R of t is defined as t, okay, for t greater than or equal to 0, and it is 0 for t less than 0. This is how the unit ramp function is defined. So how does it look like? Okay, I'm just taking the sketch of that now. Okay, so what we are doing is the sketch of R of t, and they very clearly are saying what is this? The x-axis is time. This is called as time axis. Okay, now what is R of t? R of t is t for t greater than 0. That means it only exists here. It does not exist for t less than 0, mind you. Okay, in this region it will not exist. So that is what is being told here. T is greater than 0, only it is t, otherwise it is 0. So that means it's all 0 here. So let's make it as 0. So till here it is 0. From 0 onwards, what's happening? It's t. At 0 it is 0. At 1 it is 1. At t equal to 2 it is 2. At t equal to 3 it is 3. At t equal to 4 it is 4, and it just goes on and on and on. Okay, so what is it? See, so you need to just join these points, which I'm not able to do it properly. Okay, let me try that again. Just draw it properly, you people. Yeah, this time it's good. And why it has to be called as unit? This is ramp type. This is ramp. Okay, this is ramp type. It just goes on and on and on from there on. See here, till infinity it goes on. Why it has to be called as unit ramp? Because see the slope of this. What is slope given by? This is called as slope. What is this? Is what? This is delta y, and this is delta x. Okay, slope is given as delta y by delta x. What is delta y here? See from here to here. What is this? This is 1, 2, 3. Okay, so from here y is 1. Okay, and x is also 1. So slope is what? 1. So this ramp is of slope 1. Okay, so that's why it is called as unit ramp function. Okay with that. Now, what is the Laplace transform of such a unit ramp function? Everybody understand that? So let's apply the Laplace transform on this. So what we are doing is Laplace transform of R of t. What is it given by? It is given by 0 to infinity, integration to 0 to infinity. R of t is the signal into e power minus st dt. So this is the formula now. Fine. Now it is 0 to infinity t. R of t is t e power minus st dt. Okay. Now you have two functions of t now. You have two functions of t. One is t and the other one is e power minus st. So what would you do to find the integration of this? Okay, integration by parts we call it. I hope you're better than me when it comes to integrating. Okay, so let's integrate this. What is it? So it's t into e power minus st divided by minus s, the integration of the exponential, keeping t as it is, minus differentiation of the first signal, that is t, and integration of this integrated signal. Integration of this integrated signal. What is that? E power minus st divided by minus s. Already there is a minus s. So let me write that, minus s into minus s. So how would it look like? It looks like this. So this is equal to minus 1 by s into t power minus st. Okay, then minus e power minus st divided by s square. So we have to be applying what? We have to be applying units to it. What units we have to apply? 0 to infinity. Okay, so apply the units 0 to infinity and see what we get. Okay, so if you apply 0 to infinity here, the first term will become 0. Okay, this is by L'Hospital's rule. I'll be talking about that. Maybe let me write that. This is 1 by s. The first term I'm saying. So it is infinity by infinity you will get. Okay, minus t is there, right? Then if you apply, so this is how it is going to look like, the first term. Okay, infinity by infinity you cannot do. So what we have to do, we have to use L'Hospital's rule. Okay, we shall use that in the next step. Okay, what is this doing here? It's e power minus infinity. E power minus infinity is 1 by infinity. Okay, so this is minus e power 0. What is this? This is actually 1 by e power infinity, means it is 0. 1 by infinity. Okay, so it is 0 minus, and this is going to be 1. You all understand, anything to the power 0 is 1. Okay, since you have infinity by infinity, we cannot just leave it there. We have applied the limits and we are getting infinity by infinity. Okay, and if there is infinity by infinity, we cannot take it as infinite, because in something undefined by undefined cannot be 1. Understand that? So we need to use L'Hospital's rules. What is that? L'Hospital's rules tells that whatever is there in the numerator, just have to differentiate it once. Okay, or keep differentiating till that infinity by infinity is not there. Okay, so if you use L'Hospital's rule, okay, this would become 0 if you use L'Hospital's rule. So what happens? The whole stuff becomes 0, the first term. So what would happen here? It would be minus 1 by s square, this term. Okay, uh, 0 minus 1. So this is how it becomes. So therefore what happens? Therefore Laplace transform of the unit ramp function r of t is what? Is 1 by s square. Or sometimes instead of writing that as ramps, sometimes this also is true. R of t can be directly written as t. Laplace transform of t is given by 1 by s square. Whether you say t or r of t, it's all the same. Understand that point? Why? Because see, what is r of t? R of t is t for t greater than or equal to 0. Since it is from 0 to infinity only, so r of t is t from 0 to infinity. Whereas r of t is 0 for minus infinity to 0. Minus infinity to 0 anyways we are not considering. This is unilateral transform. Understand that? So Laplace transform of unit ramp function, which is t, is given by 1 by s square. Is that okay? Now we shall take another signal now. Okay, so that is decaying exponential. Everybody take down that. The fourth one, the fourth signal that we are looking at is decaying exponential. Okay, so see here, let x of t be equal to e power at. Okay, here if a is positive, if a is positive, then x of t is growing exponential. Everybody understand that? Similarly, if a is negative, then x of t is decaying exponential. Okay, they're very particular in saying that the decaying exponential. Okay, so therefore we can say, therefore decaying exponential. I'll tell you how it looks like. Is x of t equal to e power minus at. So this is what is decaying exponential, because we have attached a negative sign. If we don't attach a negative sign, if a is positive, then it is growing. How does the growing exponential looks like? See here, the growing exponential looks like this. This is growing exponential. See, it is growing. So what is this? This is e power at. At 0, this is 1. The amplitude of the exponential is 1. This is t. So this is growing. Okay. Similarly, if you have a as negative, that is this e power minus at. Fine. This is decaying, I said, right? So how does the decaying exponential looks like? Decaying exponential looks like this, which is decaying with time t. Somewhere it becomes 0. So what is it at t equal to 0? It is 1. See, the amplitudes of both the exponentials are 1 at t equal to 0. Understand? Okay, so this is decaying, this is growing. Everybody understand that? So this is decaying exponential, e power minus at. Understand? So what is that we're looking at is the decaying exponential. Why they are particular about decaying exponential? Why they are not going with growing means? See, the growing exponential is going to infinity with t. Okay, if it any signal which goes to infinity, for such a signal we don't apply transform. Understand this. Is everybody okay with that? Not all the transforms are applicable to all the signals, and the transforms are applicable only to the signals which are finite in amplitude or converging signal. This is called as diverging signal. So this is converging with t, with increasing t, it is coming to zero. So this is diverging. Whereas with increasing t, it is going to infinity. It is diverging. This is converging. Sorry, this is converging. This is diverging. We don't apply transforms to diverging signals. Understand that? So this is another information that you can gather. So this is called as, also called as diverging signal. Okay, why it is called as diverging? With the increasing t, okay, it's going infinity. With increasing t, it is going infinity. What's happening here? This is called as converging. Why it is converging? Because with increasing t, okay, this is going zero. So this is called as converging. Understand, we don't apply transforms to diverging signal. Transforms are not applicable to diverging signals. Everybody okay with this? So when they say, they are very particularly saying that we are applying transform to the decaying exponential. That's why we have considered this. Okay, that's why we have considered this as decaying exponential. They are not asking about the growing exponential. Sorry, yeah, growing exponential we are not considering. Okay, so that is the small introduction I gave regarding the exponential. So let us now take the Laplace transform of the decaying exponential. That is what? E power minus at. A has to be negative for it to be decaying. We don't apply transforms to growing exponentials. So therefore, how does it look like? How does it look like now, everybody? Take down. It's from 0 to infinity, e power minus at, okay, e power minus st dt. Understand that? So this is how it's looking now. So what do we do after this? What do we do after this? There are two exponentials, right? So can you bring them as one exponential by combining the powers? See here, 0 to infinity, okay, e power, you can say take minus out, then it would look like s plus a into t dt. Is it okay with you? So this is how we are going to arrange the powers of the exponential. E power minus at and e power minus st were there, and we are letting it look like e power minus s plus a into t. Is that okay with you, everybody? Now, can you integrate this? Everybody go on integrating this. How does it look like? The integration of exponential is this, the same, divided by minus s plus a. Is that okay with you? Then we have to apply limits 0 to infinity. So if we apply limits 0 to infinity, how does it look like? Okay. So this is equal to minus 1 by s plus a, we shall keep out. Then we shall make it infinity. We'll apply infinity limits. That is e power minus infinity it becomes by making t equal to infinity. Okay. Then by making t equal to 0, it would become e power 0. And I've told you this 1 by e power infinity. What is this? This is 1 by e power infinity. Okay. So which is 1 by infinity, and 1 by infinity is 0. And what is this? This is 1. Okay. So therefore what we can say, so this would become minus 1 by s plus a into what? 0 minus 1. Therefore, what we can say? Therefore, Laplace transform of e power minus at is what? 1 by s plus a. Logically enough, just tell me, if this is 1 by s plus a, okay, what we can say, if you do mathematically, if you see, what is the Laplace transform of e power plus at? Mathematically, if you do, e power at plus 8 is diverging, but still if you see it mathematically, okay, what would that look like? It would look like what? Here if it is minus, it would become yes plus a. If it is plus, it is supposed to becoming yes minus a. Understand? This is plus. Everybody's okay with that? So these are certain signals that I wanted to give you. Let's see another signal now. That is sinusoidal function. Okay, so let's see the sinusoidal function. We have seen this. Let's see the sinusoidal now. Okay, so what is that sinusoidal function we are talking about? Fifth one. Sinusoidal function. Okay, how does it look like? It looks like this. Yeah, everybody just copy it down. We're taking it as x of t. What is x of t? X of t is sine omega t. Now, the sinusoidal function can be expressed in terms of exponentials. Okay, why we are interested in exponentials? Because we know what happens with the exponentials. What are the Laplace transforms of exponentials we already have derived. So if this sinusoidal can be expressed in terms of the exponentials, it would help us in getting the results fast. Okay, so this is what we're doing. We express the sinusoidals in terms of the exponential. What is sine omega t in terms of exponential? It is e power j omega t minus e power minus j omega t, okay, divided by what? Divided by anybody? Anybody, what would this be? Divided by 2j. I don't know how many of you remembered this. Okay, so this is how we can express sine omega t in terms of exponential. If you take cos omega t, cos omega t would look like this. Cos omega t is e power j omega t minus e power minus j omega t divided by 2. So for cos, it is just 2 in the denominator when you're expressing it in terms of exponentials. But if it comes to sine omega t, then it is divided by 2. I think it is plus. Yeah, right? Cos omega t is plus, isn't it? E power j omega t plus e power minus j omega t divided by 2. Whereas here in sine omega t, it is divided by 2j. Is that okay with you, everybody? So we shall see the transform of this in the next class. Before coming, if you can get that, it's good. Just the integration of these